Welcome back to part 5 of this set of videos on modal analysis. I'll pick up exactly where I left off. So we were looking, let me go back to Octave, I'll put it in the background there. And then this figure 1, I'll put it up, I'll probably just get rid of it because it doesn't tell us a whole lot. Well, it tells us that we're not going to have any vibration, but we don't need it. What we're interested in is we're interested in this figure 2. And what I'd like to show is that the natural frequency that is given here is 2 radians per second. So our period, the way we get the natural frequency is we look at the period. So I came up here and I clicked on my zoom, and then I can look at this little peak right here. So the peak before this is at 0. So if we look at this, yeah, so you can tell these straight lines are we're looking at it very closely, and these straight lines are an artifact of the simulation, which does things in time slices. What we want to know is we want to know where this peak is right here. And it looks like to me that's 4.44, and this is 4.45. So we're not halfway in between. I would say we're at, say, 4.446, because this looks like it's a little more than a quarter of the way across. So let's use that figure and see what we get. So I'll go back to Octave, and our period, which is big T, is equal to 4.446. And then we can get our omega n. It's equal to, our formula for that is 2 times pi divided by t. So it says that omega n is equal to 1.4132, and remember what we got as an eigenvalue was 2. So we square this, you can already tell that it's going to be really close to 2. So omega n squared equals omega n squared. And we get really close to 2. Okay? The reason I didn't get 2, of course, was because I read the value off of that little, no, not that, I don't want that, sorry. I read the value off the plot, and the plot, you could actually get a more accurate plot if you wanted to. There's ways to do that, but this is pretty close. So everything is in sync. All right, now something that occurred to me that I thought would be actually good to do here. What we've seen is that if you give as initial conditions the mode shapes, then you won't excite anything but that mode. Okay? Now, if you give something besides the mode shapes, you will excite both modes. So what I'm going to do, and I haven't done this yet, so if it doesn't work, I apologize, is I'm going to go back to my editor. And, well, I'll tell you what, first thing I'm going to do is kill off that figure 2, because we'll just redraw it. Now what I'm going to do here is, let's see, we'll just do it for, we don't need to run, we don't need to run it twice, because what I want to do is simply put in, so I'll pull the left one off by a negative, to the left by negative 70711, and I'll keep the right one fixed, so it's not going to move. So I actually have stretched the spring, but now I am in a it's not a mode shape, it's just some configuration that's not that mode. Okay? Now, I could comment all this other stuff out if I wanted to. I've forgotten how to do a gang comment where I can just comment out the whole thing. Well, I tell you what, we'll just run it and we'll ignore figure 2, because it's going to give us the result that it gave us before. But what we should see in figure 1 is we should see some movement, and it's going to be really sloppy movement. I got to save this because we're exciting both modes. So let's take a look at that. Let's go back to the command window. Let's go back up and run. There we go. Double MK not fixed run. Okay. And what we have here, wow, that's interesting. Let's see what's going on here. It looks like I may have only excited one mode. And there's probably a reason for that I didn't give. Yes, I've excited the second mode is what I've done. Okay. And I know why I did that. What happened was, if you look at, so 0 is, I held my second mass still and I pulled the first mass to the left. I've basically done the same thing that I did before. I've pulled the masses apart and let them go. Notice that the 0 point now is not 0, but it's well, it's going to be half of negative 0.70711. But basically, I have only excited that second mode. So I didn't anticipate that, but it makes sense once I do it. I've basically done exactly the same thing that I did before, where I pulled both masses equally apart. Well, I pulled them apart here too and let them go. So it's basically the same phenomenon, but instead of oscillating around 0, I'm now oscillating around, it's basically the average of the two initial displacements. So we've excited the second mode, but at a different location than we did the first mode. Okay, now another thing that I ask, and it's real easy to do, let's close this up and let's close the second one up. What happens if let me go back to my notes. What happens if you make the second mass double the first mass? Okay. How does this change the modal frequencies and the mode shapes? Well, one thing that I can tell you, you're only going to have two modes, okay? And the other thing that I can tell you, since it's not hooked down, you're going to have a rigid body mode. So you're still going to get a modal frequency of 0 and a mode shape that has the same deflection, initial deflection of both masses. So you'll pull it over to that spot, probably negative 0.70711, let it go, and it's just going to sit there. But how the modal frequency and the mode shape looks for the second case is not so evident. So I'm going to leave it at that, and maybe I'll make a video of that, but I think I might ask my students to do that themselves first and see what they get. And then the other thing that's interesting, there's several other possibilities here. What I would argue is that with two masses, and you can see this, you can actually kind of guess what the mode shapes are going to be. If they're not hooked down, you know that you're going to have a rigid body mode, so a modal frequency of 0 and an eigenvector that has the same deflections for both mass 1 and mass 2, okay, regardless of what the masses are. But how this changes the mode shapes, I don't, I can kind of guess I'm going to have a rigid body mode, not kind of, I can say I'm going to have a rigid body mode, and then I think the other one is going to be where the masses are just going back and forth, approaching and going away from each other back and forth, which we proved. It's not so easy to kind of figure out the modes of a 3-cart system. So try that out. I haven't done it. You can use the same values that we used up here. Have all masses the same first, and the stiffness is the same. Oh, that's one thing that we didn't do with the first one that we could do, is you could actually have a different stiffness between the two also. So there's all sorts of possibilities for, you need that down here for the three mass system, not for the 2 mass system. But if you made these stiffnesses different, then that's going to have an effect. So changing the masses and so they're not all equal, changing the stiffnesses so they're not all equal. Those are interesting things to try out. Actually, in a book that we've used, it's Sham's Outline for Mechanical Vibrations. In Chapter 11, there's a system like this. It's a 4-mass system, as you can see, very much like what we have up here. They forgot to put their wheels down here, but that's okay. And they have different masses and then also different spring constants. Okay, and this is a force system. Now they give the parameters for the force. It's 1,000 newtons per meter and 35 radians per second. So in my mind, when I look at this, well, you're going to have 4 nodal frequencies and 4 mode shapes. So it's more complicated than this system. But what you ask in a case like this is you ask, oh, is this forcing function at or near one of the modal frequencies? So you have 4 modal frequencies, and if you have a modal frequency that is near 35 radians per second, it could be that by forcing this system this way that you actually are exciting that mode. So you have to analyze that and see if that's the case. Okay, so I'm going to stop here with this set, and I may produce some more videos in the future related to this set or in this set that give answers to these problems and talk about them. Thanks for watching. Leave questions at the bottom of any of these videos, and I'll respond to them as I can. Goodbye. Thanks for watching.